students, in the previous lecture I was discussing about forecasting trend with help of regression analysis. Also I have discussed about how to build a regression model. In this lecture I will show you how to use the regression model for prediction. After that I am going to discuss about forecasting seasonality without trend and with trend. So, the agenda for this lecture is linear regression model for making predictions and using how to use regression analysis for predicting seasonality without trend and seasonality with trend. Dear students, in the previous lecture we have constructed a regression model. So, using that regression model we are going to predict. Suppose predict the price for a house with 2000 square feet. We know that our regression model is house price equal to 98.25 plus 0.1098 square feet. If I substitute the square feet value 2000, I am getting the house price value 317.85. The predicted price for a house with 2000 square feet is 317.85, all the values are in terms of 1000. So, it will be $317,850. When using a regression model for prediction, only predict within the relevant range of the data. You see that the data is from 1000 to 2500. So, if you are making a prediction just after this point, it is okay, that is a relevant range for interpolation. Suppose if you want to predict here, if that is the x value is extreme high, maybe 5000 square feet, so this model may not be valid. So, the point here is that do not try to extrapolate beyond the range of observed x values. Next, we are going to discuss about the measures of variations. This concept is used to find out the goodness of our regression model. So, here what we are doing, the total variance is made up of two parts. Here total variance is total sum of square is equal to regression sum of square plus error sum of square. I will explain in the next slides how we got this SST equal to yi minus y bar whole square and regression sum of square equal to y hat minus y bar whole square and error sum of square is yi minus y cap whole square. Here the meaning of SST is the total sum of square. It measures the variation of yi values around their mean. SSR is the regression sum of square, explained variations attributable to the relation between x and y. SSE is the error sum of square, variation attributable for factors other than the relationship between x and y. So, I was discussing about how to find out the variance. If there is no x value, the easiest way is predicting by predicting using its mean value y bar. So, this point is, for example, this point is the actual data, actual values of y. But if we use the mean of y value for the prediction, so the total error is, you see that the total distance is yi minus y bar, that is the error, square the error, then we have to sum the error. Why we are summing? So, this point, this one point is only for illustration purpose. Like that, there may be different point may be there, some point may be here, some point may be here, some point may be here, some point may be here. So, we are finding total sum of square, that is why we used sigma. So, the total sum of square is difference between actual value minus the mean value and squaring that error and summing that error. So, that is our SST. SSR is the regression sum of square. So, this distance is y hat minus y bar whole square, that is regression sum of square. And you see the top here, this portion is error sum of square. What is that value? yi minus y hat whole square. So, this error sum of square is unexplained variance. Why we are putting sigma? Because like that there are so many points, we have to add all the errors. So, here this portion regression sum of square is nothing but the explained variance. Suppose if our regression model is a good model, for example, it goes like this. Now, what will happen? The value of error sum of square will be minimum and the value of regression sum of square will be maximum, larger value. So, the model is good. So, if the line goes exactly on this point, we may say that the error sum of square is 0. So, here SSR will be equal to SST, there is no error at all, that is an ideal regression equation. Here the goodness of model is going to be explained, the term called coefficient of determination or R square. The coefficient of determination is the portion of the total variation in the dependent variable that is explained by variation in the independent variable. The coefficient of determination is also called R square and it is denoted by R square. We have seen explained variance divided by total variance. Explained variance is regression sum of square, total variance is total sum of square. The range of this R square is between 0 and 1. So, coefficient of determination R square, when the R square is equal to 1, it is a perfect linear relationship between x and y. What is the meaning of that? 100% of the variation in y is explained by the variation in the x. It may have, you see that in x axis r is there, r equal to minus 1. So, it has negative, perfect negative relationship, but the value of r square equal to 1. The bottom figure says r equal to 1, it has perfect positive relationship because the line passed through all the points, but the r square value equal to 1. Now, if the value of r square is between 0 and 1, it will not be perfect, but it will be the actual points, the blue points scattered around this line. Similarly, the bottom also scattered around the thick line, this line. So, weaker linear relationship between x and y, some but the bottom some but not all the variations in y is explained by the variation in x. So, this is somewhat good, but this is not that much good because there is a more variations here. You see, when r square equal to 0, no linear relationship between x and y. The value of y is not related to x, that is none of the variation in y is explained by variation in x. The another way, apart from the coefficient of determination, another way to test the goodness of model is, the accuracy of our model is standard error of the estimate. The standard error, the standard deviation of the variation of observations around the regression line is estimated by SSE error sum of square upon n minus 2. Why it is n minus 2? Actually, it is n minus k minus 1. So, k represents number of independent variable. In our example, the number of independent variable is the square feet of the land. So, we know that already explained how to find out SSE as yi minus y hat whole square upon n minus 2. Here n is the sample size. Comparing standard errors. So, yes, y x is the measure of variation of observed y values from the regression line. See the figure which is in the left hand side, it has the small standard error, but you see the figure on the right hand side which has the large standard error. The magnitude of S y on x should always be judged relative to the size of y values in the sample data. If you are comparing two models, the If the standard error is minimum, we can say that model is good model. And other things, what are the assumptions for regression line? We can say in short form itself L.I.N.E line. First one is linearity. The relationship between x and y is linear. Second one is independent of errors. Error values are statistically independent. Third one is the normality of the error. Error values are normally distributed for any given value of x. Last assumption is equal variance, also called homoscedasticity. The probability distribution of the error has constant variance, that is the meaning of your equal variance. So, not only finding R square and the standard error is important, the standard apart from the standard error and coefficient of determination, another way to judge the goodness of model is residual analysis, that is error analysis. Error is actual minus predicted value. The residual for observation I, EI, is the difference between its observed and predicted value. Check the assumptions of regression by examining the residuals. Examine for linearity assumption, evaluate independence assumption, evaluate normal distribution assumption, examine equal variance for all levels of x. So, the graphical analysis of residuals will help you to check this assumption. We can plot residuals, that is error versus the value of independent variables. Now, look at the residual analysis. In x axis we have x, in y axis we have residuals. Now, when you plot the error, you see that it is following a curved shape, right. See that it follow the curved shape. We can say then our assumption of linearity is violated. Generally, this will happen if the actual data follow non-linear pattern. Look at the right hand side. If it is linear, it is equally scattered around our predicted regression line. So, the right hand side is the plot for error for a linear function, the left hand side figures are the figures for non-linear function. Now, the next assumption is that the error should be independent. Look at the left hand side, here there is a trend on the error. So, that means there is a dependency on the error. But you see the bottom one, the residuals follow certain patterns. If there is a pattern in the error, we can say that errors are not independent, there is a dependency, that is violation of our assumption. When you plot the residuals, you see that it is almost equal number of points are above the x and below the x. So, what we can say that the errors are randomly distributed. So, this assumption also can be verified with the help of this plot. Then checking the normality, we can check the normality of the error with the help of stem and leaf display of the residuals. What is the stem and leaf? So, what will happen? Suppose you have error is 23, 24, 25, 26, again 26, again 25, again 25 for example. The stem is the first digit 2. So, this is 23, 2, 4, 2, 5, next 2, 6, again 2, 6, again 2, 5, again 2, 5. So, this pattern, okay. So, this portion is called stem, first digit is stem, the second digit is leaf. Okay. So, this pattern follow normal distribution, this is one way to check the normality. Next, we can check the normality using box and whisker plot of the residuals. When you plot a box and whisker plot, it will be like this. This is your Q1, this is your Q2, this is Q3, this is minimum, this is maximum. So, what will happen if this the middle lines, it is middle of the box, right, then we can say that data that error follow normal distribution. If this line on the left hand side, we will say that it follow skewed distribution, that means it is the right skewed. If the middle line is on the right side, we can say that data has left skewed data. Another way to test the normality is histogram of the residuals. So, when you plot the histogram, for example, suppose I am plotting like this. If it is, when you plot that, it is following the bell shaped curve, then we can say that error follow normal distribution. Then we can construct a normal probability plot of the residuals, PP plot. So, PP plot will be like this. If it is exactly all the values are falling exactly on this diagonal, then we can say that error term follow normal distribution. Then how to test the equal variance assumptions? The left hand side figure says that unequal variance, you see that the variances keep on increasing when the value of x increases. So, this is the violation of our equal variance assumptions. But look at the right hand side, the variance there may be increase in trend, but it is around the our predicted line. So, that is the bottom also, it is a level data, but the variance are around the predicted line. We can say the equal variance assumptions are accepted. The another way to test whether the errors are independent or not, you have to plot the residuals. So, for in our example, when you plot the residuals, you see that there is an equal number of points are above the mean, above this point, above this standardized residual value and below the standardized residual values. So, what is happening? It does not appear to violate any regression assumptions, because the error terms are randomly distributed. Now, we are going to discuss about inferences about the slope. What is the meaning of inferences about the slope? The regression equation which have used house price equal to 98.25 plus 0.1098 square feet. So, this is nothing but in the form y hat equal to b 0 plus b 1 x. Now, here the slope is b 1. The value of this slope for this model is 0.1098. Now, we have to see this regression equation is for our sample data. If you expand, if you extrapolate for the population, whether this relationship between square feet and the house price is significant or not, that we can test with the help of inferences about the slope. So, this slope value 0.1098 is only for the slope which we got from the sample data. Now, we are going to test is there a relationship between the square footage of the house and its sales price. That how I am going to do with the help of Excel, I am going to show whether the model is significant or not. So, I am going to open Excel sheet. I have taken house price and square feet value. So, go to data, data analysis, regression, okay. Select y value including y, then you select x value, there is a label, check the label, check the confidence level. Then you can see that here there is a residual is there, standardized residual is there, residual plot is there, line fit plot is there, and normal probability plot is there. When you check these boxes, you will get residuals also. So, at present we are going to test whether the model is significant or not. So, press OK. Now, you see C17. Now, I am going to interpret this output. So, what is there? Look at these values. Here I have intercept and x value, and I have standard error, and we are going to test whether this model is significant or not by looking at this p value. If the p value is less than alpha, right. So, we have to less than or equal to alpha, reject H naught. If p value is greater than alpha, accept H naught. So, in our model, the H naught, the null hypothesis assumption is this beta 1 equal to 0. The alternate hypothesis is beta 1 not equal to 0. So, if I accept my null hypothesis, there is no relation between x and y at the population level. There may be a relation between x and y for the sample data. When I look at the p value, the value of p value is, suppose alpha is significant level is 0.05. So, that means I am 95% confidence. So, the significant level is 0.05. So, here the p value is less than 0.05, it is only 0.01. So, what will you do? I will reject my null hypothesis. So, when I reject null hypothesis, I am inferring there is a relationship between x and y. I will go back to PPT. Confidence interval estimate for the slope. So, we have realized that the slope is significant. Suppose I want to find out the confidence interval for the slope. So, it is B1 plus or minus T n minus 2 SB1. For example, in a hypothesis testing, if you are predicting confidence interval for the mean, so what is the formula? You remember x bar plus or minus z sigma by root n. Here x bar is the sample mean. Similar to that, here B1 is our coefficient here, plus or minus this z sigma by root n is nothing but our standard error. Here the sigma by root n is the standard error. Similar to that, here we can see the standard error here SB1 0.03297. So, I will go back to Excel, I will show you what is the standard error for the independent variable. See that it is 0.038, sorry 0.0329, that is the standard error. We will go back. So, we know we can from the Excel output directly we can take the B1 value, then I can get the SB1 value and the T n minus 2. So, the T n minus 2, here n is the number of data set, that value I can get it from the table, but here you need not worry for that. Here we got the lower limit after calculating plus minus value, we got lower value is 0.03, the upper value is 0.18. This T of n minus 2 we can get it from the statistical table or with the help of Excel you can do that, but here the Excel itself provides the confidence interval estimate for the slope. So, the actual value is 0.10, but it can lowered down up to 0.03 and it can be increased up to 0.18. So, at the 95% level of confidence, the confidence interval for the slope is 0. This value is taken from here 0.0337 and 0.1858. Since the unit of the house price variable is in terms of 1000, you are 95% confident that mean change in the sales price is between, if you multiply by 1000, $33.74 and $185.80 per square feet of the house size. And one thing you have to remember, when you look at the confidence interval, so the 95 confidence interval does not include 0, either both the values are positive or it may be both the values are negative also, but you see that here both are at the positive side. So, we are not capturing the 0 value, but our null hypothesis is beta 1 equal to 0. So, you see that here lower limit is 0.03, upper limit is 0.180, in that we are not able to capture 0. So, there is no chance that beta 1 will be equal to 0, but it is always beta 1 will be not equal to 0. So, we are rejecting our null hypothesis. So, what we are concluding, there is a significant relationship between house price and the square feet at the 5% level of significance. Dear students, so far I have discussed about forecasting trend data with the help of regression analysis. Now, I am going to discuss seasonality without trend. Look at the table on the left hand side. There is a quarter 1, the sale is 125, quarter 2, quarter 3, quarter 4 for the year 1, similarly for year 2, year 3, year 4, year 5. When I plot the data, it is looking like a trend data, but when you closely look at, there is a cyclic variations. For example, see, look at the quarter 2 in the year 1. So, again in this data, the values are in the second quarters are always higher. For example, here it is 153, here it is 161, for third year also it is 144. So, second quarter there is a cyclic pattern, but there is no trend. So, if instead of using a regression analysis for the level data, for each quarter you can have a separate regression line. For example, this is for quarter 2, this is for quarter 2, this is for quarter 3. So, this kind of regression model can be built with the help of a regression technique called dummy variable regression. So, when you use a dummy variable regression, you can forecast values for each quarter. Instead of considering as a single data set, you can forecast for each quarter. So, what will happen when you forecast for each quarter, the overall mean squared error will be decreased. So, that will provide more accurate model. The next one is the seasonality with trend. Now, look at the year 1 data for quarter 1. So, it is 4.8, year 2 it is 5.8, year 3 it is 6. So, what is happening? There is a cyclic pattern and you see it is the keep on increasing the quarter 1 data for every year. So, here not only cyclic pattern, there is a trend also there. So, instead of doing a regression model for the trend data, so what we can do for example, here this is 1, 2, 3, 4, this is 1, 2, 3, 4, 1, 1, 2, 3, 4, 1, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, again 1, right. 2, 3, 4, 1. So, instead of predicting only trend, so you can have a trend regression line for each quarter. So, what will happen that, so that model, right, so that model will be more accurate instead of forecasting only trend. So, in the seasonality with the trend model, we are not only predicting the trend and we are predicting the trend in the seasonality also. So, here also you have to use the dummy variable regression to increase the accuracy of the model. Dear students, in this lecture I have explained how to use regression model for prediction and explained how to test the assumptions of regression model using residual analysis. Then I have explained how to test the significance of the regression model with the help of spreadsheet. I have also discussed about forecasting seasonality without trend and with trend. Thank you.